who is the professor and Canada Research Chair of Green Chemistry in the Department of Chemistry at Queen's University in Kingston, Canada. He did PhD studies in Canada and also postdoctoral studies in Japan before moving to first a position at University of California, Davis, and then in 2003, 2004, moving to Queen's University, where he is currently a professor. Multiple awards and certainly lots of interesting work, especially in switchable solvents using CO2 and supercritical CO2-based fluids. So very excited to have you today, Philip. Please go ahead and share your screen so that we can get started with your presentation. Great. And Philip will be talking to us about CO2 as a trigger for stimuli-responsive materials. Thanks again for accepting our invitation, Philip, and please, the floor is yours.
Great, thank you. I hope you can see the screen now.
Very, very well, thank you.
Yeah, okay, perfect. Thank you, everybody. Today, I want to mention some of the work I've been doing on CO2 as a trigger for stimuli-responsive materials. And that little image on the right is supposed to illustrate the overall concept that we want to make materials, including solvents and other strange materials that are not normally stimuli-responsive. We want to make them switchable or stimuli-responsive. There we go. So I often get asked, and I notice if I go to like a conference on CO2 utilization, that almost all of the other talks are talks about CO2 conversion, not CO2 utilization without conversion, which is what I'm doing. My CO2 does not get converted into anything. It just gets recycled and maybe eventually released. And so people, kind of wonder, well, why would you release the CO2 at the end? Why don't you convert it into methanol or some fancy product? And so here's my philosophy on this. If you say, well, there's two options for CO2 utilization. You can have CO2 utilization without conversion, which is what I mostly do, or you can have CO2 utilization with conversion, which has the added advantage that you're not only just using recycled or waste CO2, but you're also consuming it in a balanced reaction equation. So isn't that better? Like, shouldn't we just do that and forget about the utilization without conversion? So to answer this question, I'd like to point out that in the life cycle assessments that people have done on processes which consume CO2 in the balanced reaction equation, there haven't been so many such studies, but on the ones that have been done so far, they have found that the amount of CO2 consumed in the balanced reaction equation is small compared to the energy consumption or energy savings of the process. And therefore, the carbon dioxide emitted from the process, or savings of carbon dioxide emitted from the process due to energy. And so really, whether the CO2 is consumed in the balanced reaction equation or not is largely immaterial compared to whether we're saving energy and materials. So that's why I perfectly happily work on CO2 utilization without conversion, because as long as we use the CO2 in a way that saves energy and materials, then we are reducing the amount of CO2 going into the atmosphere. And it's not necessary to convert the CO2 into something in order to obtain that benefit for the environment. Now I need to introduce also stimuli-responsive materials. I'm sure most of you are familiar with these, but basically these are materials that switch back and forth reversibly between two states, which differ in their properties. So there's like version 1 of the material and version 2 of the material, and you can apply a trigger or remove a trigger to cause them to change from the one state to the other and back again. And a classic example you see every day is the light bulb. When electricity is applied, it is bright, and when electricity is not applied, it's not bright, it's dark. And so we're used to this so much. We use light bulbs every day. We don't think about it. But if you think about solvents like hexane or toluene, it's not switchable. It's toluene, and it's always toluene. You can't change it to something else. So that was the original philosophy when I started getting into the CO2 switchable solvents, was to make it so that solvents would change their properties whenever you need them to. And that you can't achieve with normal solvents. I've moved on from switchable solvents since that time, but the idea is the same with my research. Can we have materials change their properties whenever we want them to? And can we have that happen in a way that makes a process or a product more energy efficient or more efficient in material usage? And so why can't we have like switchable solvents, switchable surfactants, switchable surfaces? Why can't we make all sorts of chemicals and materials change their properties upon demand? And why can't we use that to save energy? So there's lots of triggers. There's lots of literature on stimuli responsive materials out there. And most of the papers, and in fact, I found review books about stimuli responsive materials that don't mention CO2 at all, which is kind of disappointing, but still, most of the focus has been on light and voltage as the triggers to cause things to switch their properties. Light is nice because it's not toxic, it's not accumulating in your system, it doesn't make chemicals build up in your system, but its disadvantage is it takes a lot of energy and it requires your material to be transparent. Otherwise, the light's not going to get in. And the functional groups that are light responsive are generally expensive. Voltage, again, voltage is not toxic unless you electrocute yourself, and it doesn't accumulate in the system, but it requires your material to be conductive or it won't work. Acids and bases can also be used. You can throw acids and then, hydrochloric acid, sodium hydroxide in your solution. It causes a nice big pH swing, and that's very easy to get lots of materials to change from, their acidic form to their basic form and vice versa. But the disadvantage here is strong acids and bases are toxic. Every time you cycle the material, you're creating salt waste, and that salt waste can accumulate in your system unless you have some added expense step in which to remove it. And then you've got more waste material. And so that's why I like carbon dioxide as a trigger. It's not toxic. It's not accumulating in the system. So you can switch your material many times and your system doesn't get dirtier and dirtier. The disadvantage of CO2 is compared to acid and bases, it's a small pH swing. We don't, sodium hydroxide and hydrochloric acid can give you a pH swing of 14 units. CO2 can only give you a pH swing of about 2.5. So it's much weaker. But the fact that it's non-toxic, non-accumulating is worth it to go with a smaller pH swing. It's a good exchange. And the other thing is most of the reactions that we do, the switching process is mass transfer limited. The actual reactions themselves are reasonably fast. It's just getting CO2 into the material and back out again is the slow step usually. So what is a CO2 switching reaction? Well, there's many of them, but this is the one that's most commonly used. It's you have a basic material, which could be an amine. That's the most popular choice, but it could also be something like a phenolate anion or a carboxylate anion. But let's stick with amines for the moment because that's the most popular choice. We have an amine, which is indicated here by the blue letter B, meaning a base. And you expose that to CO2 in the presence of water and the base gets protonated and giving you a bicarbonate salt. And in order to make sure it's a bicarbonate salt and rather than a carbamate, we use a tertiary amine or a bulky secondary. If we have a non-bulky secondary or primary, we get carbamate salts instead, and that's not desirable because it's harder to reverse. So the blue state where the amine is still neutral, this is going to be a non-ionic basic material, relatively hydrophobic, less soluble in water. That solution in water is going to be low ionic strength. But if you look at the red state where the amine has been switched into the bicarbonate salt, now it's ionic, it's acidic, it's hydrophilic, it's more soluble in water, it's got the aqueous solution is a high ionic strength. Lots of different properties have changed, way more than is listed here. And because the reaction is relatively reversible, all you got to do is flush the CO2 away with some air or mild heating, and the reaction goes back. And so we really do have the ability to switch the material from state number 1 to state number 2 and cause its properties to change as a result. And no elevated pressure or anything is required. And so basically the blue state is what you get in regular water, and the red state is what you get in carbonated water. And so we've made different materials that respond to CO2. I don't know if you could see my cursor or not, but in the upper left, we have the organic solvents that change from low polarity to high polarity and back again, sort of like having, diethyl ether become DMSO all of a sudden, or methanol. And then you can make it go back to being diethyl ether again. Now, it's not diethyl ether, but it's solvents of that kind of low polarity changing to solvents with very high polarity and back again. And that's useful for lots of things that I'm not going to talk about today. We have switchable hydrophilicity solvents. These are things that are kind of like hexane. If you mix it with water, you get two phases because the solvent is hydrophobic. But if you add carbon dioxide at 1 atmosphere, suddenly the solvent is miscible with water in all proportions or most proportions, like methanol in water, for example. And so that's really useful for lots of different things because these solvents can be removed from any product by just extracting it out with carbonated water. So you don't have to distill your solvent away from your product anymore, because that takes a lot of energy, right? All you can do is extract your solvent away with carbonated water, and then you can bubble air through the carbonated water to get your solvent back out and reuse it. So this saves a lot of energy because you no longer have to distill organic solvents to get your product away from the solvent. Switchable water on the far right, I'll talk about this in more detail. It's an aqueous solution that changes its properties, whether it's ionic strength, osmotic pressure, density, solubilizing ability, all sorts of things that are aqueous solutions. I'll talk about them in more detail. Bottom left, we have switchable surfactants. In one version, it is a surfactant. In the other version, it's not. And so we can have surfactants function and then not function. And that's really useful in things like latex paints, where in the paint can, you want the surfactant to be functioning to keep the particles from merging in the paint can. But once you apply it to a surface, then suddenly those surfactants are problems, they're not helpful anymore. You want the particles to merge to make a continuous film on the surface you're painting, and you want the surfactants to turn off. And so they do. Thanks to CO2 switching, we can make surfactants that turn off when the latex paint is applied to a surface. Switchable surfaces and particles. We've had flat surfaces like aluminum or steel sheets that can change their hydrophilicity or hydrophobicity. We've got particles that can change, like chromatographic columns. The packing will change its properties as the run proceeds because we're introducing CO2. Switchable paint, lots of examples there. And in each case, the advantage is that the properties of the polymer are changing when the paint is applied to the surface. So the polymer might be water soluble in the paint can, but once it gets applied to the new airplane or whatever you're making, it changes to water insoluble, and that makes it a water resistant coating. So we've made it, my collaborator, Michael Cunningham, and I wrote a book about it. It came out a year and a bit ago. There's been so much activity since we started this. Lots of other people have jumped into the game, and it's been quite fun. Now, I want to tell you a couple of stories before my time is up about different applications of the switchable materials. So, for example, if you want to make something like a polymer or a fuel or an organic chemical, you want to make it out of biomass or out of fossil fuels, which one is greener? We would think the biomass is greener because it's sustainable, right? But actually it's not. If you look at the life cycle assessments that have been done for this kind of comparison, it's always the fossil fuel that's greener. There's less environmental harm caused by converting fossil fuels to organic products than there is from biomass. And it's not a small difference, it's a huge difference. And this is horrifying because we all want to use sustainable feedstock. Biomass conversion sounds wonderful, but actually biomass conversion is usually far more harmful to the environment than fossil fuel conversion. Why? You might think it's because of the different structures of the chemicals, and that's not the case. The reason is because of water. When you play with fossil fuels, you don't have to remove water. It doesn't have much water in it. You don't use the water as a solvent to convert it, so there's not much water removal required. But when you do biomass, it comes in water. A lot of biomass is grown in water, like algae. When you convert it, it's done in fermentation or acid catalysis in water, and you end up with product in water, and then you have to separate that by removing the water, usually involving distillation of water. And you know what that's going to do. That's going to put the energy cost up because the heat capacity of water and the heat vaporization of water is so high. So this is why biomass conversion is not green. And if we want to have a sustainable society in the future, we need to be able to get water away from products without hurting the environment so much. This is crucial. And so we've been working on using the switchable materials to try and solve this problem. So for example, if you have this, this is switchable water, the one I mentioned on the far top right in the earlier slide. So switchable water is just an aqueous solution containing an amine, and an example amine is shown on at the bottom. So it's mostly water with a little bit of amine in it. That's a pretty good solvent for organics, not because water can dissolve some organics, but because the amine really helps organics to dissolve in the water. But if you add CO2 at 1 atmosphere, that amine becomes a salt, a bicarbonate salt, and it salts out the organic. And so now the organic is not soluble anymore. So this solvent on the right, where the amine has been changed into its bicarbonate salt, we call this the polar version or the ionic version of the switchable water. So this solution changes back and forth between a good solvent and a non-good solvent for organics. And so you can make products precipitate out. They'll be soluble as long as CO2 is not present. But as soon as you add CO2, the product precipitates out. You don't have to distill the water and therefore have a huge energy cost. You can do this at room temperature. And then you can switch once you've recovered your aqueous phase, you can get your amine water back and use it again. And here's an example of solubility of caffeine as a test organic solute. You can see that when CO2 is absent, it's quite soluble, but when CO2 is present, its solubility drops by a couple orders of magnitude. So you can really precipitate it out and recover it. Now, this is useful for separating organics that are weakly hydrophilic. But when we tried to do things that are more hydrophilic, we found it didn't work. They didn't come out when we added the CO2, which is really disappointing because these are some reasonably valuable products. And so what we found is if you increase the CO2 pressure, they come out. So it doesn't work at 1 bar, but it does work at 2, 4, 10, 20 bar. And suddenly these things are coming out. And so we've checked the energy calculations, at least the preliminary energy calculations show that this is lower energy cost than distillation. But what about those really hydrophilic compounds like ethanol, methanol? Ethanol is a major product from biomass. And right now it's being recovered from the water by distillation, which is terrible. And so how can we get the ethanol out of the water? And so we tried the high pressure CO2 for the switchable water and it didn't work. So what we're doing now is we're using supercritical CO2 to extract the ethanol from the switchable water. And that's working really well. That's in progress right now. The paper's not ready yet, but we're hoping to get that in relatively soon. So that's looking really promising. We haven't got the full LCA done yet, so we can't tell you for sure that the energy cost is lower, but it's looking promising. Another thing we've been doing with the switchable water is looking at its osmotic pressure. I mentioned that many different properties of these aqueous solutions change when you add CO2 or take away CO2. So if you have that amine in water, and it doesn't have to be the amine I showed before, it could be almost any tertiary amine or bulky secondary. When you add CO2 to that, the osmotic pressure rises because you've got more species in solution. And this osmotic pressure rise can be quite large, like orders of magnitude. And then you can make it go back again. So what could this be useful for? Well, imagine you have some wastewater or salty water on the left side of a membrane, and you put one of our switchable water solutions on the right side of a membrane. And in this case, it happens to be the bicarbonate salt of trimethylamine. Okay, and then you, because our aqueous switchable water solution is very salty, the osmotic pressure is very high, it sucks water out of our wastewater. And I've only shown a small water reduction here, but actually you can get our wastewaters down, 5 to 10-fold down by volume. And you get rid of the wastewater. Disposing of the wastewater is the cost of that disposal is proportional to volume. So shrinking the volume of the wastewater is very valuable. Now, the water that's been recovered, you can't drink it, it's got amine in it. So what you do is you get rid of the CO2, and then the amine comes out. Either it precipitates, or if it's a gas like trimethylamine, it simply comes out with the CO2 and you can collect it in a condenser and use it again. Or if it's a soluble polymer, you can just recover it by reverse osmosis, which is cheap because the osmotic pressure is so low once the CO2 is gone. So we made a company out of this. It's called Forward Water Technologies. They built a pilot plant in Alberta. They've got 2 operating plants in India and are building operating plants in North America. It's been going really well. Switchable drying agents. We're making drying agents. If you want to pull water out of organic liquids like fuels, you don't want to spend too much money getting the water out. And so distillation may not be desirable. You can put solid absorbents in there. And so if like you can take a molecular sieves or something like that, you guys do it in the lab all the time, I'm sure. You throw it into the organic solvent or fuel and water mix, and the drying agent absorbs the water and gets, saturated. And then you pull the drying agent out and now your fuel is dry. But when you try and regenerate your drying agent, it takes a lot of heat, a lot of energy. So you're really not saving much energy. So we need to figure that out. So what we need, this problem is that the drying agents are water absorbing when you want them to be water absorbing, but they're also water absorbing while you try and release the water. And that's the problem. So we need a switchable material that will be water absorbing while it's doing the drying job, but it'll be water repelling when you try and do the recovery, the regeneration of the material. So we want a drying agent that will spit the water out when we're in the regeneration step. So we make silica particles with polymeric amines stuck to them that are hydrophobic. This is water repelling, but if CO2 is present, then it's water absorbing. It absorbs the water from the balanced reaction equation, and then it absorbs about 70 more water molecules because of the change in polarity and ionic character. So we're getting about 80 water molecules per nitrogen, per amine group here. To absorb. And then when you regenerate it, we only have to use 50 degrees to regenerate it, whereas molecular sieves don't work. Even silica and alumina, which are easier to regenerate, they remove much less water than our switchable agents. Finally, last one slide here, we can make catalysts, heterogeneous catalysts that change their mind as to what they want to give as a product. So this catalyst is rhenium nanoparticles on silica that has the switchable polymer coating on the silica particle. And there's an electron microscope picture for you. And if you try and hydrogenate, for example, this particular substrate, which comes from biomass, if you have CO2 absent, you get the red product. If you have CO2 present, you get the blue product. And that's because the CO2 actually gets converted to formate by hydrogenation when the CO2 is present, and that actually blocks, we believe it's blocking some sites on the surface of the catalyst and giving it different selectivity. But if you remove the CO2, the formate decomposes and you go back to the other selectivity. So in summary, I think I've run out of my time here. So recycled waste CO2, I really believe, can be a trigger for all sorts of different kinds of stimuli responsive materials. And by making such materials for applications where switchability is needed, we can save energy in materials, we can separate products, and we can facilitate recycling of wastewater, we can facilitate recycling of plastics and this kind of thing. We've got lots of different examples of that I don't have time to tell you. So I hope that was interesting, and I thank you for your attention.
Thank you very much, Philip. Wonderful. So yeah, now we have a good amount of time for questions and discussion. I see. So maybe I'll get started. First of all, this is a really interesting approach. I was wondering if you have, if you can say a few words about the requirements for the amines that you use in connection with the CO2